Hey, what's up, Ziguanas? This is day 19 of the 30 days of Z Coding Challenge. Join me one more time as I apply over 2 decades of professional programming experience and around 15 years of code teaching experience to master a new language, Zig. My name is Dusan. Welcome to Zignited. Before I start with today's topic, I would just like to one more time say the plan for tomorrow is to do one regular streaming like this one, so for day 20, and I will also do one special where I will for the third time code, so working on a small tic-tac-toe game for the third time, and that will be the last time I will work on tic-tac-toe. So next time, in probably 5 days, I will do something new. Okay, so let's go to the docs one more time and let's do result location semantics. A lot of text, but let's read. During compilation, every Zig expression and sub-expression is assigned optional result location information. Yeah, this is so theoretical and abstract. So every expression or sub-expression is assigned optional result location information. Yeah, so we'll see what they exactly mean by this. This information dictates what type the expression should have. The type of the expression, okay. Its result type. And where the resulting value should be placed in memory. Its result location. Okay, got it. The information is optional in the sense that not every expression has this information. Assignment to underscore, yeah, we use that for dumping. For instance, does not provide any information about the type of an expression, nor does it provide a concrete memory location to place it in. Okay. As a motivating example, consider a statement const x u32. Let me try to zoom in a little bit. If I zoom in more, it will jump to some other. Okay, it's close enough so that it's more visible. Now I can go even larger. Okay, just for the sake of readability for you guys. Okay, here we were. Consider statement const x u32 equals 42. The meaning of life. The type annotation here provides a result of result type of u32. Okay, to the initialization expression 42, instructing the compiler to coerce this integer, initially of type Comptime integer, yes, to this type. Okay, we will see more examples shortly. Then the next thing, this is not an implementation detail. The logic outlined above is codified into the Zig language. So it means even if you had multiple different implementations of Zig, this is something that is always the case, no matter how you implement Zig. And its primary mechanism of type inference in the language. The system is collectively referred to as result location semantics. Okay. So for now, the basic idea that I understood from this is just to understand what will be the type of expression and where it will be stored in memory. Result types. Result types are propagated recursively through expressions where possible. For instance, if the expression address of E has result type pointer to U32, then E is given a result of type U32, allowing the language to perform this coercion before taking a reference. Okay. So first coercion, then taking the reference to it. Okay. The result type mechanism is utilized by casting built-ins such as int cast. Rather than taking as an argument the type to cast to, these built-ins use their result type. So yeah, that's why you don't have to specify an argument how you want to cast, because they have their built-in sorry, not built-in, but this result type to determine this information. The result type is often known in context where it is not the as built-in can be used to explicitly provide the result type. Okay, makes sense. We can break down result types for each component of a simple expression as follows. And by the way, I'm reading docs. I mentioned this before, but in short, I'm learning Zig, so I don't have much of Zig experience. I have exactly 19 days, actually 18. This is my day 19 days of Zig experience. So I'm documenting the process of me learning Zig. And I do have a lot of experience with dozens of different languages. So this is kind of the idea, to show how someone with previous experience with many different languages, different kinds of languages, would approach learning. And with Zig, it's also, let's say, specific because it's not so popular like some other languages, and the resources for learning it are much more limited than the others. So that's why docs are a good starting point. Okay, let's go back to docs. We can break down the result types for each component of a simple expression as follows. Let's see what they want to do. And I will copy this code before examining it. And this is what I did yesterday here. So let's delete all these. I will also delete these prints here. And I don't need this mem for now, but let it stay. Maybe I'll need it later. So let's see what they want to do. They create one constant. They call it val, which is u64. And then they have 1, 2, 3 assigned to it. So this is basically Comptime int, course to u64. Then they create another constant. They call it s, which is of type s. So that is, I'm just looking if I missed this line here. So first of all, they create the constant s, which is a struct, and it has this field. One field, x, which has the type of u32. Then here they did what I just explained. They create another constant. They call it val. Then they create a third constant, which is of this type. And then what they assign is this is anonymous structure. And inside of that structure, they reach into the field x, and then they set it to, and then they call the built-in function int cast. So they call this function to cast it to integer from this value, which is already integer, right? But they are just like using this mechanism that is the focus of today. And let's see what they write here about the result types. So this part here, which is here, has result type s due to the type notation. Yes, because that's what is annotated here. The part here, which is this inner thing, has result type of u32 due to the type of the field sx. Yeah, so it's analyzing here. So it sees that it should assign the value to the field x of this struct, and in the definition of the struct it's written that it's u32. So that's why compiler will know that it should convert into that type, and it is u64 at this point here. And val, so here, or actually maybe they're speaking about this line here. Yeah, so there I believe they are destructuring this expression here. So they refer to the val here. It has no result type as it is permitted to be an integer type. So they, I guess in this expression, they speak about the result. Yeah, so the result type makes sense only if there is an expression. So yes, then for sure they're not referring here, because here it's, I mean, yes, this is an expression, but it's explicitly annotated what is the type. So yeah. And let's see what they try to test here. They expect this to be equal. So what is the output of this and s.x? which should be the case. And I will test it in a bit different way. So I will print just the value of it. So let's say equal IQ for short for equal, and then here I will put this and this, and I will compare them with equal operator, and let me comment out these. Run. Yeah, it's true. Okay, let's see what's next. Result type information is useful for the aforementioned cast built-ins, as well as to avoid the construction of pre-coercion values and to avoid the need for explicit type coercions in some cases. The following table details how some common expressions propagate result types. Cool. They will give example of expressions where x and y are arbitrary sub-expressions. Okay, let's go through these. This is interesting. So expression, parent result type, sub-expression result type. So in this expression, const val of any type equals x. There is no parent result type, and x is a t. So sub-expression result type. Okay. Then the next one, var value. So this is just like different kind of variable. So here, not variable, but identifier. Here it's constant, here it's variable. And it's the same case. So no parent result type. X is a type t. Then val equals x. Then x is a type of val. So yeah, here it will, because we don't explicitly. So here the point between this third, like the difference between these two first and the third one is that here when you explicitly say the type, state the type, then that will be the type of sub-expression. And if you don't specify the type, if you don't annotate it, then under the hood they call type of for this value, right? And then they will coerce it to that type. And of course, this works in the combination. So this is assuming that you already have defined var and it has to have a known type. Then let's see here as type, comma, x. Again, no parent result type. Sub-expression x is of this type. Yeah, because we explicitly say type here. It makes sense. Then the address of x, pointer to t is the parent type. Okay, yeah, because we always do this when there is already x defined. And then when we say in expression that we need a address of x, then the parent result type will be pointer to t, and x becomes t. Actually, x is a t already, but here the pointer to that type will be the parent result type. Okay. Then the same example. Parent. Okay, got it. So they are just saying this is not like what will be the result. This is what happened before, basically. Let's say like that. Simplify. So if you had before, let's say in expression, something that is a pointer to t, then if you do the address of x, then this is going to be the sub-expression result. And if you had a slice of t with the same operator address of x, you will get a different sub-expression result type. It will be some array of type t. Okay. Then during the function call for x as a parameter, x has the type of the first parameter of the function. Yeah, makes sense. So whatever is defined in a function as the type, from this expression, x will be inferred that it's of that type. Then this is anonymous structure, right? So if we put x in anonymous structure, or actually they call them tuples. So if they are anonymous structures, but another name that they use for them in Zig is tuples. So when you have a tuple which has x inside, and the parent expression type, how they call it, result, sorry, parent result type is t, then x is std meta field type. Oh, this is a bit more advanced. I haven't researched this meta. I remember I used this few times, maybe, if I'm not mistaking it with something else. But we can see here what is the point here. So field type of this tuple or structure, however you want to call it, and then it takes the type t, because that was the parent result type, and another parameter here is this dot at, and this is explicitly saying, if I'm remembering correctly, this is saying like get me the first field of the struct. Like this entire thing means that, if I'm not mistaken, if I remember correctly. Then we have a bit more advanced situation here where we so yeah, I guess this is the case, because here we never say dot field equals x. We just put a value, right, the variable in this case, and then that's why they want to see what is the first field in the struct or tuple, however you want. But in this case, we explicitly say we want to interact with the field .a in this struct or tuple, and we set the value of x to it, the same parent result type like in the previous example, and then they have a bit different interaction here. So field type, now they explicitly say .a, because we said here that we want that specific field, so they don't take the first field, but whatever, it can be second, third, that doesn't matter. It's the, I mean, in this case, the order doesn't matter, the name matters. Here, e and curly brace, so this is, I believe, something like an array. If I, so this is a part of the array expression, I don't know if you just have, yeah, this is the array, I believe. So x inside of an array of type t, no parent expression. Again, field type, like this case here, the same. So these are on the hood the same. Then for the next example, which is kind of similar to this one, and then it's the same like this one. So I'm not sure about this, because array usually has curly brackets in front and the size, and then type, and then curly braces. I forgot what is this without that prefix, so maybe it's not an array. I forgot. Okay, let's go to the next type built in. When you ask the type to give you the type of x, then x is standard built-in type. Okay. Then type info for the input of x. X is a type. I've never, like, this is so weird for me. Why they say type is type. A bit abstract for me, at least at this level of my Zig experience and knowledge. So this is bit shifting right to the left. If you say I want to bit shift x for y times to the left, then they say y is under met log to anti-sealing, okay, type of x. Yeah, again, a bit weird. Type of x. So they take the type so that they see what is the sealing for that integer. Then log to in seal y log 2. Okay, so don't understand at this point. Let's move on. Result locations. In addition to result type information, error expression, and by the way, let me do one thing that I don't go further away than what I wanted. So I will just copy paste here the documentation, but not for arrays. Yeah, now if I zoom in, I'm zooming in everywhere. This is like weird on Chrome. And here it hasn't changed. So let me just double check something before I continue. How far should I go with this assembly? Okay, so result types, then result location. So basically using namespace is the first chapter after result location semantics. Okay, so once I get to this, I will stop for a second. Result location, so this is the second of the two chapters of okay. In addition to result type information, every expression may be optionally assigned a result location. Yeah, so this is like the second half of the story. A pointer to which the value must be directly written. The system can be used to prevent, so basically, yeah, we are speaking about two things here. What is the type and what is the pointer, what is the address where it will be stored. This system can be used to prevent intermediate copies when initializing data structures, which can be important for types which must have a fixed memory address pin types. Okay, so this is interesting performance-wise, because if you don't need to copy things, you just refer to them. That will save some time. When compiling the simple assignment expression x equals e, many languages would create the temporary value e on the stack, and then, oh, I love this like low-level explanations how things work. So most of the languages would create the temporary value e on the stack and then assign it to x, potentially performing a type coercion in the process. Zig approaches this differently. The expression e is given a result type matching the type of x and a result location of address of x. For many synthetic forms of e, this has no practical impact. However, it can have important semantic effects when working with more complex syntax forms. For instance, the expression dot blah blah blah, okay, equals x, b equals y, has a result location of pointer. If this is the question, if this expression has a result location of pointer, then x is given a result location of address of that pointer dot a, and y respectively address of that pointer dot b. Without this system, this expression would construct a temporary struct value entirely on the stack and only then copy it to the destination address. In essence, Zig desugars the assignment foo equals the same expression to the two statements foo.a equals x, foo.b equals y. Okay. This can sometimes be important when assigning an aggregate value where the initialization expression depends on the previous value of the aggregate. The easiest way to demonstrate this is by attempting to swap fields of a struct or array. The following logic looks sound, but it in fact is not. And let's see, they will get some error, and then they will explain maybe. No, they will not. But the error says, so I will then even not run this code because we'll just like get the same error. Let's try to see how it works without running it. So they create a variable, they call it ARR, so array, 2, length of 2, so array of U32s with 2 elements, and then they assign with this like anonymous structure, they assign 1 and 2 to that array. Then what they say, array equals dot array1. Good evening, Robert, how are you? And yeah, so basically what they said, they want to swap. So because this used to be the index 0 and this used to be, I mean here, index 0, index 1. So they basically want to take the value of the second element. And here they want to take the value of the first, basically trying to swap the array. the previous line is equivalent to following two lines. Yeah. So this fails. This will succeed. This will fail. And what they say, attempt to swap array elements with array initializer. Okay. Return error text. Okay. Yeah, they don't explain why this fails. Aha, okay, it fails the value. Okay. So they will basically... No, I thought the code will break, but code will not break. It will just like not swap. So logically it's wrong code, not that syntactically. Syntactically it's not wrong. So it will compile, will run, but the effect will be that you will have the double value of... So you will have 2. So you don't swap elements, you just override the first element with the second one. So that's why, that's what they actually wanted to say. Okay. Understood. The following table details how some common expressions propagate result locations, where x and y are arbitrary sub-expressions. Note that some expressions cannot provide meaningful result locations to sub-expressions. Okay, even if they themselves have a result location. So let's see, expression, result location, sub-expression. So this is different. Before it was like, in this second column it was parent result location, now it's result location. Let's see, expression const val of type t equals x, sub-expression result. The x has result location, which is address of val. Okay, yeah, so they're just speaking now about the result of the result locations. The second one, variable called val of type t equals x. So here it's constant, here it's variable, and the same. Result location will be address of val. Okay, val equals x. So this is assigning the value after it's declared. So you already have val before declared. X has result location of address of val, the same. Okay, then here, and if the address is pointer as type t and x has no result location. Address of x when it's pointer has no result location. Function x when it's pointer has no result location. Tuple x pointer has result location. It takes the pointer, then the first element there, and then the address of it. Okay. Then the similar thing, but when there is a named field, then the similar, it's address of a pointer.a. Then in this case, type, and then curly braces x for the same pointer. Result location has no result location. Typed initializer do not propagate result location. Okay. So similarly here, typed initializers do not propagate result locations. Then type of x has no result location. Type info, the same. So this is again logical shift, bitwise shift for y of x. X and y do not have result locations. Okay. Yeah, basically because it's needed. Whenever it's not needed, it will not take space in memory. Using namespace. Using namespace is a declaration that mixes all the public declarations of the operand, which must be a struct, union, enum, or opaque into the namespace. So let's see. Const s equals struct, using namespace, import std. Then try s test inspect true. So they just put anything that you just can see if this runs. Okay. So basically they just inject the namespace here. So it mixes all the public declarations of the operand. So here basically, because we have this as an operand, it will take everything that is this std module, or however they call it, everything that is public, and mixes it up so that it is available in this namespace. Okay, as an important use case when organizing the public API of a file or package. So they call it package basically. So std, maybe it's called package. Still not sure about semantics in Zig, how they name things. Okay, for example, one might have c.zig with all of the C imports. C import, and they include, yeah, this .h. I remember these header files from C. So these two and the third one here, and this looks like a constant, but I forgot what is it. stbi only png, stbi no stdio. Okay, an interface or something. The above example demonstrates using pub to qualify the using namespace. Additionally, makes the imported declaration public. This can be used to forward declarations, giving precise control over what declarations a given file exposes. Okay. Okay, yeah. So chain reactions and control, full control. Comptime. Oh, we're already there. Comptime. Double check here. Yeah. So let's see just here to have an overview of the chapters. So first, introducing the compile time concept. This is the first thing. Then it has three subjects, compile time parameters, this one. Then compile time variables. Then, yeah, this is longer. Did I miss the third one? Generic data structure. So yeah, I probably missed the compile time expressions. So I'll try to cover all three of them if I have time today. If not, I will try to at least do these first two. Okay. Comptime, Zig places importance on the concepts of whether an expression is known at compile time. There are a few different places this concept is used, and these building blocks are used to keep the language small, readable, and powerful. Comptime parameters. Comptime parameters is how Zig implements generics. It is compile time duck typing. So they have three functions. The first one only has comptime, right? Yeah, the other one and the third one they don't. So comptime t type, A is t, B is t, return the same type t, and returns if A greater to B, else B. So A in this case, else B. Give me the bigger float, give me the bigger integer. So then this one has A, which is F32, B F32, result F32, returns max of F32, A and B. So they call this one here. Okay, so that's what they meant of generic. So basically you create a function that will work on the type that is, let's say, understood at the compile time. So then at the compile time, you are basically taking, in this case, this type F32. So it will then be adjusted that it has two F32 integers as unsigned, F32, not integers, F32 floats as parameters. It will return also F32, and then it will compare them here and return which one is greater. And if you do the same call with, so not the call even, this is definition. So you define another function with different types, and then it will be able to call this one, like here, because of Comptime parameters. Zig types are first-class citizens. They can be assigned to variables, passed as parameters to functions, and returned from functions. So assigned to variables, passed as parameters to functions, and returned from functions. However, they can only be used in expressions which are known at compile time. Aha. Okay. So basically, they want to say that generics are compile time only in Zig, if I understood correctly. Okay, which is why the parameter t in the above snippet must be marked with comp time. Okay, now it makes sense. Comp time parameter means that first, at the call site, the value must be known at compile time or it is a compile error. And secondly, in the function definition, the value is known at compile time. For example, if we were to introduce another function to the above snippet, there would be an error. Let's see what is the difference. So they had the same start, but they changed something. Let's see. So max compile t type a t t t. This is the same, so it must be here. This function is different. So full condition bool void const result equals max if condition f32 else u64. Aha, so they are playing with the type, and then so they kind of like not option, how would they say that? I don't use something that is a keyword or concept in Zig. So they choose the type dynamically here in this function call during the call to max, and then they get this error because it will depend on some condition that is known during the runtime. So when you call this during the runtime, you basically decide what is the type, and that's why this breaks, because this has to be known at the compile time. Okay, this is an error because the programmer attempted to pass a value only at runtime. Yeah, what I said, a function which expects a value known at compile time. Another way to get an error is if we pass a type that violates the type checker when the function is analyzed. This is what it means to have compile time duck typing, for example. Aha, now they change only this max. Let me pay attention what they did. Comptime t type, a t b t, t is the return type, return if a, a else b. What is different? I missed a difference. A t b t, so comptime t type a t b t. Comptime t type a t b t, return t, return if a greater b, a else b. Yeah, it's the same. So what is? Aha, here they call. I'm blind. Okay. Try to compare bools. Boolean, true, false. And what is the error? Aha, here, because they try to say Boolean greater than other Boolean. Yeah, not allowed for type bool. On the flip side, inside, aha, so it checks. I'm just like want to go back. So because this is then during the compile time, it will see. It will first of all replace this type, which is generic, with a specific one, and then it will also test, for example, in this case, if the operator is supporting the type all during the compile time. That's cool, that's cool. It doesn't pass this to a runtime. Flip side, inside the function definition with the Comptime parameter, the value is known at compile time. This means that we actually could make this work for the Boolean type if we wanted to. Let's see what they want to say. Aha, so now they changed the code, so that's what they meant. So the signature is the same here, but the condition is different. So they test if the type equals to bool, and this is so cool that you can actually make it flexible depending on the type. So return A or B. Else, if A greater than B, return A. So this is literally like, you know, it's not bool, and then you just take the and still it will break for some specific type. So this will not break if the type is a numerical one, which supports the operator. But as long as you the moment you pass something that is not supporting this operator, it will break again. Okay. Else if A return A, else B. Okay. And they all pass tests. Cool. This works because Zig implicitly inlines if expressions when the condition is known at compile time. Aha. And the compiler guarantees that it will skip analysis of the branch not taken. Cool. So that means it's even more optimized during the runtime. You'll have smaller code, so it will not compile all the pieces. So this is basically kind of like a dead code. For example, if it's a bool, it's kind of dead code, and it will not even be included in the binary. Okay. This means that the actual function generated for max, yeah, literally like what I said. It's going to optimize the binary. The situation looks like this, yeah. All the code that dealt with compile time known values is eliminated, and we are left with only the necessary runtime code to accomplish the task. This works the same way for switch expressions. They are implicitly inlined when the target expression is compile time known. Okay, now I even understand. I remember trying some other examples before, and I skipped when they said inline because I did not know what they mean by this, but now I understand what they mean inlined. Okay. Compile time variables. Okay, this is the second of the three, right? Subtopics in Zig, and let me just check the time. Yeah, it's okay. In Zig, the programmer can label variables as Comptime. This guarantees to the compiler that every load and store of the variable is performed at compile time. Any violation of this results in a compile error. This, combined with the fact that we can inline loops, allows us to write a function which is partially evaluated at compile time and partially at runtime. Yeah, that's interesting. Let's see what they do here. Okay, so view const. So this is a struct, this is an array, then 3 functions, 4 functions, and then they do things. I just want to see first on high level what they do. Let's see now one by one. So the first one is a struct, 2 fields, name and func. The first one is a slice, constant slice of U8s. The second one is a function which takes I32 as a parameter and returns I32. So this is like just a signature of a function, right? Just to say how the struct instances are going to look like. And this is called cmdfn, this struct, okay? Then they say cmdfns as an array of basically unknown size, or let's say, I don't know how to say this properly. If they say officially this is unknown size or dynamic size, or how they will call it officially. Then they take the type from here, that will be the type of an array. Then they create 3 instances of this struct with specific values. So the field's name get 1, 2, 3 string literals respectively, and the func fields, they got 1, 2, 3. So this is the reference to these 3 functions down there for sure. I haven't read yes, but yes, 1, 2, and 3 are the names of these functions. So they put them here. Then all the functions are basically similar, as I can tell. The signatures, of course, are the same because that's defined here. It has to be with one parameter iterate2, and it has to return iterate2. And the implementations are all so very similar. So they just like this one increases by 1, by 2, and by 3 respectively. So they just return the same number increased by 1, 2, or 3, depending on the function. Inferred size, compiler looks at how long, I'm reading now Robert's comment, compiler looks at how long the array is, and that will be the size. Aha, so this is like Comptime inferred. Okay, okay, got it. Thank you, Robert. Okay, okay. I forgot that detail. So let's see the main function here. I mean, not the main, but in this case, the one that is most important. It has Comptime prefix character. Then U8 is the type of that. Start value is i32. It returns i32. Then let's see what they do. Var result of i32 type equals the start value from here. Comptime var I equals 0. Okay, this is known at compile time. And then inline while, and while starts here where it ends, just to see, I think here ends here. Okay, so this is inside of the while, which is inline, and the while does what? As long as I is lesser than cmd fns len, and that's in this case basically 3, and this is the cmd fns, so basically it will repeat that many times how many elements are in this array up there. So what it does, it will increase the I by 1, and then there is this question inside the while. If cmd fns of I dot name 0 equals prefix character. So basically you take in here the prefix character that is arbitrary, so whatever you want, and it will be to compare to the current array element, which is a struct. So for example, in the first loop this one, in the second one this one, and so on. So it will go inside of that struct's name field and take the first character. So name field and take the first character, so OTT in the first, second, and third loop respectively. And if it matches the one that is specified here during the function call, then what they do, they set the result to, again, the same struct that is analyzed in that cycle. They take the func field and call the function with the result. And the result has this starting value. So they basically update the result. So if they don't find any matches, the result will have this starting value, and that will be returned from this function. But potentially they can change it every time this is true. And then they will take the starting value result, call a specific function, and that will increase it by 1, 2, 3, depending on which cycle and how do you match. And that will be here updated as the result. Okay. Then they try to test it 3 times. That is first with T and O and then W. So for the T, we have 2 matches. So it should change 2 times at that for that input. For O, it's only once, and for W, we don't have any match. So basically, for W, it should be 99 because they passed 99 and you don't change it, and it should be 99. For O, it's only ones. So if you say 0, 0 plus 1 is 1, right? And then here, and O is the first. That's why I remember it's plus 1, because I remember it's the first one. And for T, if you pass 1, this will happen 2 times. So it will basically call this one and this one, which are these two. So it will increase first time by 2, second time by 3. And that's why 1 plus 2 is 3, and then plus 3 is 6. So it should pass all 3 tests, right? Yeah, all tests passed. Okay, so now once I went through the logic, Mauricio Rojas. Thank you, Mauricio, for being here. So let's see. So the logic is now understood. Now let's see the topic, Comptime evaluation. So let's see now what they actually did during the Comptime and how they combine it with the runtime. So this one has a Comptime prefix character, which means that these literals have to be known during the Comptime, and obviously in this case they are. That's why the code didn't break in the first place. And because this is known at Comptime, then also here this variable is known at Comptime. So that's what they say when they say that's what will happen here when we say inline while. It will basically during the compile time inline this function, this loop, and it will do all these things all during the compile time, right? Because all these are literals, so literal known at compile time, prefix here. Yeah, so if I'm not mistaken, all this will actually happen during the compilation time. And then if you inline the while loop, basically you will also run the while loop during the compilation time. Okay, let's see what else they say. This example is a bit contrived. What that means in English, contrived. Let me Google it up here. Yeah, I'm not sharing this screen, sorry, so just for a second. Contrived meaning. So they say deliberately created rather than arising naturally or spontaneously. Okay, so basically they made it for showcasing something. Because the compile time evaluation component is unnecessary, this code would work fine if it was all done at runtime. But it does end up generating different code, yeah, of course. In this example, the function perform fn is generated 3 different times for different values of prefix char provided. Okay, let's just compare them all at once if I can. And I'll zoom somehow that we can see all 3 of them if possible. Oh no, too much. Yes, how can I? Okay, now it's visible. So first time, second and third time. Start value I32. So I just want to compare. All the signatures are the same, of course. Then the return result is always there. So the last line is always the same. Bar result I32 equals start value all 3 times. Okay. Result equals 2, result 3 is a result. Here, yeah, so this is only what is different is here they're calling the functions 2 and 3 for the same result. Here they are calling it only once, and this function 1, and here they're dumping the result. So this is basically what they're explaining what happened here in a nutshell. Okay. Was it first T? Yeah, so yeah, because I analyzed in different order, that's why I thought that they made a mistake here, that they swapped, but actually in my mind, made I analyzed from bottom to top when I looked at the code. So yeah, this is the result of the compilation, basically. Okay. Note that this happens even in a debug build. This is not a way, and this is also interesting, like this different kinds of build in Zig and the differences. So I just remember there are like few of them. I don't, of course, know at this moment all the details and how they are changing the compilation, the binary. This is not a way to write more optimized code, but it is a way to make sure that what should happen at compile time does happen at compile time. And what should happen in Vegas, yeah. This catches more errors and allows expressiveness that in other languages requires using macros. Generated code or a preprocessor to accomplish. Yeah, this is very interesting solution. Yeah, in Rust you have macros. Okay, Comptime expressions. In Zig, it matters whether a given expression is known at compile time or runtime. The programmer can use Comptime expression to guarantee that the expression will be evaluated at compile time. If this cannot be accomplished, the compiler will emit an error. For example, this part here, Comptime exit. So they call the function exit at Comptime. They try to, at least. So Comptime call of extern function exit. Comptime keyword forces Comptime evaluation. Comptime. Okay. So you can call during the compilation time basically what they are doing here. What they are doing here. So it's not an external function, it's here in the same code that is being compiled. I believe that's the reason why it's safe in this case. I'm just trying to think which kinds of functions you can call and which ones you cannot call during the comp time. Let me see what Robert wrote. You can do a lot with just this ability to evaluate code at comp time, together with the ability to use types directly and even generate them directly during comp time. Yeah, it's very, very interesting. I even like it at this level that I'm just like scratching the surface, but then I imagine that in the real implementation it would be very, very useful. It does not make sense that the program could call exit or any other external function at compile time. So this is a compile error. However, a comp time expression does much more than sometimes cause a compile error. Is there a way, Robert, my mind trying to brainstorm this topic, is there a way that you can do something like this? Like if you want to call an external function, but if you can somehow pre-cache it or something, is there a process or anything that pre-compile it or something like that? Like, pre-compile the result of the call or something like that, so that you can use it while compiling some other modules, if you know what I want to say. Let's compile. However, a compiling expression does much more than sometimes cause a compile error. Within a Comptime expression, all variables. So what I meant, something simple, not like exit maybe, or I don't know, but let's say that you have some very simple functions that have maybe only constants. For example, let's say a function that will say 1 plus 3. Like you have parameter A, parameter B, and you just like return A plus B, something like that. So something that basically can be contained and even pre-compiled. And if there is a way, you can plug it in this expressions Comptime. So basically, maybe if you already have some binary that's compiled, something like that. That's my question. All variables are Comptime variables. In Comptime you can't, but you can create a build step. Nice. In build Zig that precompiles it and enables it to some file, which is then used at Comptime. Okay, perfect. Thank you. Let's see what they say. Within Comptime expression, all variables are Comptime variables. All if, while, for, and switch expressions are evaluated at Comptime or emit a Comptime error if this is not possible. Okay. Okay. I'm just thinking like while and if for branching reasons. If and switch for these branching reasons, because some of branches can have some unpredictable results, and while and for, yeah, you can also change if you have some continuous or breaks, you can have some also situations. So understood why this is necessary. All return and try expressions are invalid. Unless the function itself is called at comptime. Okay. All code with runtime side effects or depending on runtime values emits a compiler error. This is understandable. All function calls cause the compiler to interpret the function at compile time. Emitting a compile error if the function tries to do something that has global runtime side effects. Okay. So if they're not trying to change some global states, then there shouldn't be problem. Okay. This means that the programmer can create a function which is called boot, and both at compile time and runtime with no modification to the, this is also interesting. Yeah. There's Fibonacci recursion. So let's see function itself first. So it takes one parameter called index, which is u32. It returns u32 as well. Then the question is, if index is lesser than 2, return index. So basically you have 1, the first number. Then return Fibonacci, so it recursively calls itself for the number decreased by 1 plus the call again, recursive call with the same number decreased by 2. So not this is the index, so I'm saying the number, but I understand why the idea is that you have index of something, that you have Fibonacci numbers calculated, and then they have these two tests here. So they test if Fibonacci, when you input 7, gives you 13. So basically this is the 13. Let me see. The first Fibonacci is 1. I think the second is 1 as well. I don't know how they officially order them, but let's say that first one is 1, the second one is 1, then 2, then you have 3, that's the fourth one, then you have 5, that's the fifth one. So 5 is fifth one, yeah, that's interesting. Then you have 8, which is the sixth one. Then you have 7th, which is 13. Yes, so this is the 7th Fibonacci number. Okay, just like wanted to double check. Fibonacci. Okay. I was wondering like why they test the same, but here they do it during the comp time. Yeah, so cool. This function can run both during compilation and in the runtime because it doesn't touch any global things. It just like has an input, transforms the input, and provides the output. Okay. Let me see what you wrote. Sorry. Comptime could 100% call external functions, but then you could be hacked by it. Yeah, true. So Zig team decided that this kind of stuff will be possible, but only as the build step. So you can be sure there is no malicious code outside of build file. Malicious meant as hurting you during compilation. Thank you for the explanation. Okay. So now I understand why they call it index book, because this is literally like they want to say the seventh Fibonacci number, not the number 7 in a Fibonacci sequence. And there is no 7, is not one of Fibonacci numbers. So that makes sense why they call it an index. Okay. Same as other, I will just read what Robert said. Same as other unsafe stuff like inline assembly, high operations, or ETR for, Peter from int calls. Okay, okay. Yeah, understood. So basically inline assembly, you can do who knows what. Like you have full control. High operations, again, you can read from some, you can execute things and so on. And pointer from integer, yeah, basically then you would be able to jump to specific parts of memory or read something that you shouldn't and things like that. Okay, okay, makes sense. Imagine if we had forgotten the base case of the recursive function and tried to run the tests. Okay, they commented out the base case, which basically makes it never-ending call. And then what they say, overflow of integer type. This was also one of the things that I was thinking about, because I know, for example, in Python, when I create a recursion, and if I deliberately want to do something like this, so I don't have a base case, you have settings in Python. So I use the official version of it, so because there are multiple implementations. So the one that I use is from python.org, the official one. I think it's, how could they call it, CPython or Cython. They're different implementations that are written in C. And anyways, this one, this version, when you run recursion, by default it's 1000 calls. So it doesn't, you don't have the problem of overflows, because in Python there is no specific integer size that you use. So there is no overflow basically. The only limitation is how much memory you have. So you have integers that under hood combine multiple integers. So if you need like, I don't know, 256-bit integer, you can have it. If you have 512 bits necessary, you can have it. So you don't have any size specified, because it's all under the hood. They're like merging several integers to make a big one. So you don't have this problem with overflow of the type, but you have these uncontrolled recursions. And by default, in this version of Python, which I have, it's 1000. So if you have 1000 recursive calls, it will break the code. But you can change this in settings. So you can say, I want 2000, for example, depending on your algorithm. Maybe you will need actually to call something 1000 times. So I was thinking about these things because I did yesterday, I think, a small recursive function here in Zig. And it crossed my mind, so I didn't investigate, I didn't search to see what are the limitations, if there is some number of calls that is the maximum number. But of course, in this case, because you have overflows, this will happen first anyways. So if, okay, depending on the operation, but numbers can grow very fast sometimes. And in this case, they just like let it run without the base case, which eventually made this number too big for the type of U32, and it broke the code. The compiler produced an error, which is a stack trace from trying to evaluate the function at compile time. Let me just see. This is because here they do it with Comptime. And what would have happened if they tried this in runtime? Luckily, so let me see what you guys wrote. Jorge, welcome. Let me see what you wrote. Infinite loops also have max depth for evaluation at Comptime, and you can change it to. So you speak about Zig, right? So you're referring to Zig. Luckily, we used an unsigned integer, And so when we tried to subtract 1 from 0, it triggered illegal behavior, which is always a comp time error of if the compiler knows it happened. But what would have happened if we used a assigned integer? Yeah, because here they are doing this, right? They are decreasing. And that's the reason. And where it was 0? Aha, okay, recursively it was going down, down, down. They start with 7, they decrease by 1 or 2, so depending on the branch in recursion, so eventually it became 0, and then it decreased 1 from 0, and because it's unsigned, it cannot be lesser than 0. Okay, that's what I wanted to say. And let's see what is happening with sign. So I guess it will just reach the minimum value that is for the type, and it will break again. Yes, thank you, Jorge. Where are you from, by the way? Are you from Latin America or you're from Spain? Let's see what they have here. So they just changed the type to integer 32. Robert, let me see what you wrote. Sign integer or just use overflow addition. Both get you to the recursion cap. Aha, yeah. Compiler is supposed to notice that evaluating this function at comp time took more than, here it is also, 1000 branches, and thus emits an error and gives up. If the programmer wants to increase the budget for comp time, it's nice how they call it a budget. Comp time, yeah, because you're basically budgeting your resources. Budget for comp time computation, they can use a built-in function called set eval branch quota to change the default number 1000 to something else. Yeah, it's interesting how two different languages have literally the same default, 1000. However, there is a design flaw in the compiler causing it to stack overflow instead of, I mean, I'm laughing because of course I knew what it was before the website became famous, but nowadays when someone says stack overflow, you don't think about the stack and overflow in the language, you think about the website instead of having the proper behavior here. I'm terribly sorry about that. Yeah, that's cool. I hope to get this resolved before the next release. Nice. Okay. So I will read about this just for fun, but let me first finish this part. Jorge, Guatemala, so Latin America. Oh, nice, nice. So I've never been to Guatemala. The closest part of that part of the world I've been is Costa Rica. I went there in November. So I loved it. And I was planning to visit your country and some other countries in the region, but simply I didn't have time for all of my wishes to come true. Me encanta América Latina. Let's see, what if we fix the base case, but put the wrong value in the expect line? So they do have the base case, but basically the same idea. So because it will try to match the number, and it will try to reiterate until it reaches the number. And this is probably not even a Fibonacci number, so it will never reach it. And then it will eventually overflow. Even if it's a Fibonacci number, but it's too big that it cannot be calculated in this number of times, it will be the same, right? So let's see what they say here. Container level. At container level, outside of any function, all expressions are implicitly comp time expressions. This means that we can use functions to initialize complex static data. For example, let's see. Container level, again, I have to see what they mean by container level in context of Zig. All expressions are implicitly comp time expressions. this means that we can use functions to initialize complex static data. And there is this short example. Let me see what you guys wrote. Robert, you wrote sign integer or just use orthogonal addition. Yeah, I read this. What get to the recursion cap? Guatemala. By the way, this apology is there for 3 years already. Okay, so I mean, I understand they have higher priorities and probably not too many people working, not enough people working to deal with these issues. Probably they have something that is more a bigger security issue or something. I've also seen somewhere, I forgot where I was like going quickly through the docs to see which topics I covered and what to do next. I've seen somewhere it's written like to do. So there is a missing part of the docs, but again, understood. So this is for this version. Maybe they have the same section for a previous version written. So maybe they changed that part and then they want to update the docs and they still haven't had the time. First 25 primes, a constant called that. First primes 25, and this is the function that they actually call here. And sum of first 25 primes is probably they're going to call, yeah, the other one. And they pass the address of the first 25 primes, so of this function. So this is simpler. I will just check this one first. So this sum receives a const slice of i32s, calls it numbers, returns i32 a single number. They say result is of type i32 equals to 0, and then they return it if they don't change in this for loop. And in the for loop, what they do for numbers, so they are looping through this slice here. They take every specific member element of that slice, and then they say result plus equals x. So they just add it to the sum. So they start by 0. That makes sense why it's 0, because they want to summarize. What did they do with this? They have the reference to the result. So I said it wrong, so I didn't pay attention. So this is not the reference to a function. I quickly read, so this is the reference to this, not to this. So it's a reference to the result, which will be provided by calling this function here. And I guess then this one is returning, yeah, the slice. So it's a address of slice. That's why they take it here as numbers. So this is a slice that they take from here first when they call the function. Okay, and what the function will do? First first n primes. Comptime n, okay, usize, returns the slice of n i32s. Oh, this is the array, not a slice. So the first var prime list is i32 of size n. They set it to undefined. Then the second variable is usize. They set it to 0. The third one, test number i32 set to 2. Then they return the prime list, which is this one. Okay, and then they have a while loop here. Let me see what you guys wrote. The docs are a bit old by now. Andrew said he wants to fix them once the incremental compilation and rewrite of I/O writer and reader interfaces is completed. The rewrite requires new stuff. Yeah, it's always the stuff problem. In compiler to be made. POC is done though. Good to know, good to know. So they are working. I didn't doubt it. While next index, which starts from 0, less than prime list length. Okay, so for basically all of the elements, they will do this for test number. They increase it by 1. So they, for some reason, they decided to start with 2. Probably arbitrary. Then let's see what they do inside. Test prime index. They define this variable. What of use size type? They set it to 0. Is prime is equal to true. So they assume it's true, that it's prime. Then they have a while loop, which will solve while inside of while. Test prime index lesser than next index. And next index is the same one from here. So they take... Aha, okay, so now I understand why they started from 2. Okay, because they are about prime numbers, so no need to start lower. Test prime index plus equals 1. Okay, so this is this one. Then if test number modulus prime list with this index, test prime index equals 0, they then know that they can divide it by this number, so it's not prime. And they break, because it's enough that they prove it once that it's not prime, so it doesn't, they don't need to repeat and continue. But if it doesn't break, it doesn't mean that it's a prime still, so they have to test for the next number and so on. And then finally, if they go through all of the numbers and it's still prime, so they haven't proved wrong, then they say if it is prime, then they take the prime list, the next index, and append basically this test number, and then they increase the next index by 1. Okay, so basically they are making a list of prime numbers, and then they are summarizing them, right? This is the idea. So here they do the first 25 prime numbers. They first find them, get the list which contains them. I mean, the list, I call it list because they call the variable list, but the type, of course, is this one here, it's an array. And then once they find first 25 numbers, prime numbers, they are summing them up using this other, which basically this one can summarize any list of numbers. That's why they call it sum. It will summarize all of them, no matter which are they. And then they, so I will believe them that this is the sum of first 25 prime numbers. But what is important for this case is this Comptime expressions. So we can use functions to initialize complex static data. So in this case, they are talking about prime numbers. So this can get called during the compilation so that it saves time. Then basically, if you want to generate prime numbers, this is a nice way to do it before the runtime, that you already have it in your system. And this one doesn't use any Comptime restrictions, but it doesn't change any global state, so that's why I guess this is working. So const known at compile time can call this because it is not touching any global things. Okay, when we compile this program, Zig generates the constant, with the answer pre-computed. Here are the lines from the generated LLVMIR. Internal name address constant, so 25 times I32, so it will take, it's cool how they say I32 and then the number I32 and then the number. So we can see the first 25 prime numbers. Oh, 97 is one of them. Never thought of. And then here they have the sum, which is also a named address constant of this. Okay. Note that we did not move. I'm completely imagining the words now and reading what I want to. Note that we did not have to do anything special with the syntax of these functions. For example, we could call sum function as is with the slice of numbers whose length and values were only known at runtime. Yeah. So that is cool. Cool feature. You kind of have like double usage for any, I mean, not all functions, but if you write them in a specific way, they can be used both in compile time and runtime. Let me see what you guys wrote. Okay, nothing new. Nice. So let me just see the bigger picture here. Generic data structures and case study, your favorite, Robert. So let me check the time. I think this is already taking 1 hour and more. Yeah, almost an hour and a half. So then I will stop here. At least I went through all these 3 subtopics in Comptime. Then we have the next topic here are generic data structures and case study. Let me see how big they are. Data structures. Oh, this is short. So definitely tomorrow I will cover the case study print in Zig part. And let me just double check how long is that one. Yeah, this one is a bit longer, but it's okay because the first topic is not that long. And then we come to assembly. Cool. So this is then for tomorrow. Then tomorrow I will also see that I first stream the tic-tac-toe practice part before the regular day. No, actually no. Today is 19. So then I wanted to do, yeah, maybe I will do it before. So yes, I will do day 20 tomorrow. I will think about it. Maybe I will do first day 20 normally and then tic-tac-toe, or the other way around. I'm not sure, because I kind of wanted it to be after 20 days, but it's not that important. It doesn't have to be. Just like human obsession with round numbers, nothing else. So that's the plan for tomorrow. I will do the regular stream plus the summary. Like for the third and last time, I will play with tic-tac-toe and I will optimize it. More not optimize that much, but the point is that I practice these things that I've learned after I did it for the last time, like 4 days ago, right? So I will play with new things, add them to the tic-tac-toe, and then I will wrap tic-tac-toe game. So I will not deal with this one I think at all anymore. So the next time I do some coding practice, it will be a different thing, not tic-tac-toe, so some other thing. And I will see if I can do something more complex. Okay, that sounds like a plan for tomorrow. So see you guys tomorrow. Thanks one more time for being here. Let me just see what you wrote, Robert. You can make the native setup on some pretty day number. Yeah. That's a nice idea. Thank you, Robert. Thank you, guys, and see you tomorrow. Bye-bye.